So our new objective is parametric equations, which is supplemental, optional material based on stuff we did before you left. Disclaimer. So a definition of a parametric equation is a graph of the ordered pairs x, y where you separate the x and y. But when you separate the x and y, you're saying that every x component can be a function, right, determined by a function. Every x coordinate and every y coordinate can be determined by another function, and that those functions are in terms of another variable called t. T is the parameter. And when you think of parameter, you kind of, I guess the easiest thing to think of right now, parameter is your hidden variable, and you'll see what I mean by that when we go to graph. T does usually stand for, in applications, T, shockingly, does stand for time. So these curves can get very interesting because they don't have to pass the vertical line test. So that's number one reason when you think of, well, why do we need parametric equations? There's lots of reasons, but for very, very beginning, I like to deal with and have a way of dealing with non-functions, kind of forcing them to behave like functions or be able to treat them like functions, because after all, most of our math theorems all are function based, right? If I have a function, then. So what if I have a way of taking something that's actually not a function but writing it and treating it as if, at least piecewise, it's like functions? So kind of cool, right? So here are some weird looking, right, equations. They kind of look like vectors, which is what we've just been doing, right? So if you would get your calculator out, I don't expect you to know what any of these things look like right now, but I do want you to see that what this is saying is that every x coordinate can be defined by this function. This is a function in terms of t, right? If you want the x component, if you plug in a t, a time, usually, I can get the x component. And then the y component can be found by 3 times the sine of my time parameter. So if you get your calculator out, and go to your mode, and go down here and put your calculator in parametric mode. And if you put your calculator in parametric mode, then just hit y equals and look what you have. This one equation needs to have an x component in terms of t, this one graph, and a y component in terms of t. If you wanted to also graph a second parametric equation, you need both an x and a y component in terms of t. So let's just put in this first one. 5 cosine, and hit the x button, but look what happens. And 3 sine t. Usually, I usually, when I'm in regular rectangular, which is XY mode, I'll hit zoom 6 and set a standard window. For parametrics, I usually start with zoom square. That's only my starting place. Look at that shape. Number 1, is it a function? I don't think so. Is it a circle? No, that's right. What other conic section I didn't have in the warm-up? This is an ellipse. Hit your window and look at what happens. You have a t-min that was automatically set for you. 0 to what? What do you see there? 2 pi, right? T-step was how often they're counting time for t. And my x-min and x-max set to negative 15 and 15 and 10 to 10. Negative 10 to 10, excuse me. Right? And I can manipulate from here, but this is usually the window I start with. Sometimes your t-min and t-max don't go, don't start this way. It doesn't really matter. But if you're not seeing a graph you want, sometimes what I do is manipulate my t step and say, like if you just count your t in terms of 1, right? Sometimes you get a very, very not smooth looking graph. Right? Look what happens when I change this to a 1. What the heck? Right? Kind of crazy. So before we investigate that, let's look at these things again. So here's the, whoops. Oh, see, my t didn't change when I did z5. If I do what if I do z trig? What happens? Zoom trig. Oh, snap. Oh, what the heck? Why is that? My t is still going to 1. So there's something to do with this t interval that cuts off my graph. Look what happens when I hit 2 pi again. Oh, I get the whole ellipse. And I shrank my window a little bit, my x min and x max, to get kind of a big picture. Notice what happens when you hit trace. There's 3 things here. When time is 0, x is 5 and y is 0. So notice that it's the t value that determines your x and your y. So if I wanted to say, oh, what about when t was 1, right? Remember when I only let my t window, in the window, when I only let my t go from 0 to 1, I only got this part of the graph. Interesting, right? So when I want to look at the other ones, right, you can put these in. Let me put this one in. I'm going to put t cosine t and t sine t. What kind of graph do I get there? Oops, sorry. I don't know why there's a... Oh, my Lanta! I didn't get to see it graph. But look at that pretty thing. See what happens when I hit zoom square. Got a little bit more of it, right? So you can see by messing with your window, you can get more and more of a picture. But isn't that pretty? I wonder what would happen if I made this go to 4 pi. Oh my goodness, right? Really pretty. So I'll leave it to you to play with the rest of these equations, getting practice entering them and just getting, right, practice putting them into your equation and getting a window. The last 2 are pretty famous. They're called les Zhu Figures, which is French. And you can look these up, right? Google les Zhu figure and see what makes them special. But there's some pretty cool scientific applications to these figures, which is why they're famous, right? All right. So, without your calculator, first, let's look at these parametrically defined figures. Now notice that these parametrics I've written in a different form, but it's still, I have x in terms of t and y in terms of t, right? So what the heck? I want to graph them on the given intervals, and I've changed my interval of t. So I made a box here, made a table, and I'm just going to do the first one. Again, without a calculator first. What do you get when you plug in, using these definitions, what do you get when you plug 3 into the x function? I'm sorry, negative 3. Right? If you plug negative 3 in, you get 9 plus 4, aka 13. How about when you put negative 2 in? Negative 1, 0, and 1. Now let's go get the corresponding y components when you put negative 3 into the y equation, what do you get? Well, negative 3 times negative 3 is usually 9, I think, right? So we get 9, 6, 3, 0, and negative 3. Truth? Now what happens? Let's plot these points. When x is 13, let's say that's somewhere up here, y is 9, dot. When x is 8, y is 6. When x is 5, y is 3. And when x is 4, I have 0, and then, hey, when x is 5 again, y isn't 3, it's negative 3. So I think I get something like that. Let's verify with your calculator. So let's go to y equals, and my x component is t squared plus 4, and my y is negative 3t. And again, I'm going to hit my zoom 5 window, see what happens. What the heck? Oh, right. My t is supposed to go from negative 3 to 1, silly. Oh, what the heck? So negative 3 to 1, and actually I should be, what kind of x's was I getting, right? I really don't need any, right? I didn't have any negative x's. My x's went to what, 13, so maybe I'll take this to 15. And what did my y's do? My y's went, right, negative 3 was the lowest, and what was my highest? 9, so maybe I'll make this 10. Now let me hit graph. Oh, gee, that kind of looks what I drew, right? So now what's going to happen? What do you think is going to happen when you, right, shrink this interval, right, negative 3 to 1, I shrink it to negative 2, but I go all the way to 3. And I don't really have to make a table anymore. Let's just go change the window and see what we get. Negative 2 to 3. Oh, And again, notice what happens when I hit trace. Right? As soon as I get to t equals 3, notice I can't go any further. Right? And the reason I can't get exactly to 3 is my t step. Let me make my y min negative 10 as well. And then let's go change this to negative 3 to 3. See what we get. Can you predict what you're going to get before you hit graph? Oh, snap. There's my sideways parabola. Again, notice that my t starts at negative 3. If I wanted to go further to the left, it wouldn't let me. But notice what is my x and y component. Hey, how about what if I hit trace 0? What am I going to get? Yep. How about 1? I mean, the calculator's just doing what you did to make this table. It's not smarter than us, but it's a heck of a lot faster than us. So the idea of this slide was to tell you that my time interval, right, it's my hidden parameter. So when you're graphing, when we had that graph here, right? And if we do think of the parameter t as time, when I think of the point here, 4, 0, when did the point when did this, think of a point traveling along here, at what time did you get down to the point 4, 0? Right? That was at time 0 here, right? What time did you get to the point 5, 3? When did you get here? When is the question you can ask now that you have, I'm looking at the graph x, y, but I have another or a third parameter, t, that I can use to describe points on this curve. Interesting. And notice that each of the separate components, the x component is a function, the y component is a function, right? But my actual graph is a non-function. What's going to happen here? If my horizontal component is defined by cosine and my y component is defined by sine, can you think about what that means? So kind of sort of think of x as going right and left. So if you have a particle that is being pulled to the right when cosine is positive and pulled to the left when cosine is negative, but at the same time being pulled up when sine is positive and down when sine is negative, what are you going to get out of that? Yep, our old friend the unit circle, it never goes away. So kind of sort of think like when t is equal to 0, what's going on? When t is equal to 0, cosine of 0 is 1, but sine of 0 is 0. So that's down here, right? As time increases, right? As time increases, isn't it true that cosine is going, in quadrant 1, is going to be positive? So you're trying to move right, this particle is trying to move right, but at the same time that sine is trying to pull up. So your particle kind of sort of follows this path, right? And then in quadrant 2, cosine is trying to pull you left, but sine is pulling you still up. Kind of crazy, right? That's how I travel along the unit circle. Oops, sorry. But how interesting is it that I can describe a circle with x squared? Remember, I know that the actual equation in just xy terms, right? If I think about this as my xy plane, we call this rectangular form. X squared plus y squared is equal to 1, right? Is the equation of a circle with a center at 0, 0 and a radius of 1, right? This equation gets me all the points on the circumference of the unit circle. But so does this at particular time. Again, if you go to your calculator, and I hit zoom 5, I mean, I get a circle, but look at that. What about zoom trig? What do I get? A little bit better. But you can go manipulate your window. right, and make your x min and your x max, right? What if I make this 0 to, it takes to 2 pi? And then I make this go from negative 3 to 3's maybe. Because my screen is rectangular, this kind of looks a little stretchy, but notice what happens when I hit 0, when t is equal to 0 and at 1, 0. As you move, right, changing time and increasing time, sine and cosine determine the position on the unit circle, on the circumference of the unit circle. Cosine and sine of time. Crazy. So now I need to teach you, about eliminating the parameter, because this is parametric form, right? And parametric form can also be written like this. Right, either way. And what we call sometimes rectangular form, right? This is parametric form. Or parametrically defined is another way we say that. But you're used to seeing this equation in what is commonly called rectangular form, right? Where you don't have any hidden parameters. One equation. Rectangular. One equation with just x and y. I can get x by itself or I can get y by itself. So what if somebody gives me parametric and I'm like, thanks very much, but I don't want parametric. I don't recognize that. I want to get rid of the t's. So step 1, and I want to just get my normal xy back. Solve each equation for t. That's a little bit of an oversimplification, right? Sometimes I do need to solve each, but not always. So I'm going to underline each and put a little question mark underneath of it, because I don't always need to solve each. Sometimes I need to make a choice. Choices make kids uncomfortable, I know. Especially in math class. But let me show you what I mean by that. So I'm going to take the x first and get y by itself. Sorry, my slate is giving me some problems, which is why I'm pausing here. So I'm going to go to the x equation, and I'm going to say, right, this is where I'm going to simplify this instead of saying x of t. X is equal to 4 minus 2t. And I'm just going to get t by itself, right? Which of course I can write like this. Yes? So I'm now going to take this t, and remember these are two equations representing the same graph. So this t is the same. So can you predict what I'm going to do now? I didn't have to solve each equation for t, right? I only had to solve one for t. And now I'm going to take this and put it in here and say y is equal to, I'm already starting to feel comfortable. Do you see why? Ha, pun intended, why? When I simplify this, I get negative 1/2 x plus 7. Oh, hello, old friend. I recognize you. You are a slope. You are a linear function with a negative slope. So it's a little bit flatter than normal and with a y-intercept of 7. Well, isn't that cool? So I didn't have to solve each. My decision here right? It's a little difficult to put into a recipe because sometimes my recipe changes. So my step 2 is, right, sometimes if you only solved for one, you plugged into the second equation. To eliminate the parameter t. Well, this was the nicest case possible because firstly, I am more comfortable with y equals. So I got y in terms of x here, right? Y in terms of x makes me very comfortable. But it was very easy to get x by itself, right? I got a fairly simple expression getting x by itself, and then plugging into y here was, again, not a strenuous exercise. Let's put this into our calculator and see what we look like. So I go here and I put 4 minus 2t, and then t plus 5. Now don't hit graph yet. Go to your window, right, and think about what I want to see. Since you already know what this looks like, right, I know you're not comfortable with t min and max yet, so leave that alone. But you have a linear function. It's supposed to be a linear function with a y-intercept of 7 and a slope of -1/2. So let's make your, right, x min and x max maybe again go from -10 to 10. And your y min maybe also -10. Let's go a little bit higher than 10. It's y-intercept of 5. I'm sorry, y-intercept of 7. I got part of it. Why is that? In regular rectangular land, this should go on forever, right? It should go across my whole window. What's stopping me? What's stopping this graph? Oh, I made time equal to 0. So time didn't start until 0. And when you plug 0 into the x component and the y component, you get the 0.45. What if I wanted more of this graph? What would I do? Sure, make your t-min negative something. Excuse me, right? And I could get more on the right or left by just increasing my time intervals. So hopefully you're thinking about your time as not only a hidden parameter, but kind of sort of a limiting parameter as well, right? Because I don't get my entire picture unless I take care of time. That's what makes the trig functions nice, right? Since oftentimes trig functions trace over one another, right? The periodic piece. Sometimes only graphing 0 to 2 pi is all I need. All right, let's go on. Let's practice this. Eliminating the parameter. Let's practice this skill. This time, same objective. I just gave you, right, showed you a different form of how to present a parametric equation. right? But the x component is defined in terms of t, and the y component is defined in terms of t. So I don't want the t, so I want to try to eliminate this. But notice what the issue is this time. When I try to do step 1, right? Step 1 was solve each. And remember, I always have a question mark next to each. Do I have to solve each? Do you see the issue with the x expression? I might cry. Right? Because trying to get t by itself is going to give me a plus or minus square root issue. Well, all right, maybe I'll solve for y. This one sure looks simpler. So I have x is equal to 3t squared minus 1, and y is equal to 4t. Well, this is sure a lot simpler, right? T is simply equal to y over 4. And this is pretty easy then to put in here, isn't it? And what do I have then? Careful. Oops. Right? Well, what is this? Oh, I forgot. I mean, in the last, right, the last screen, I did say what the graph was. I didn't write it though, right? This ended up to be, right, y equals negative 1/2 x plus 7, right, which is a line, diagonal line. So here, what is this? Now maybe you see why I did the warm-up, hey? That's called planning. Right? Do you recognize that? Squared. But who is squared? It's not x squared, it's y squared, which means this is a parabola, but it opens either right or left. What's the sign on the dilation factor? So this is a parabola, a non-function parabola. Opens sideways to the right. Pretty cool, huh? And again, you can put this into your calculator and see the parabola and think about what window you would need to get the sideways parabola. All right, let's do another one of those. So, remember, oh, I should have filled this in, that 2, since I only solved for 1, step 2 is the same as before. Sub into the other to eliminate t. And then I should be able to look at the equation and identify it. All right, so let's look at this one. Maybe you already have an idea what this is going to turn out to be, but I'm going to pretend that you don't. So firstly, I was a little bit worried, right? Solve each equation for t. I'm going to break the rule here a little bit. And I'm going to say, not just for t, I'm going to solve for cosine of t. So when this equation, when it said solve each equation for t, in each of the other two examples, I did only choose one, and I kind of chose depending upon what was, easiest or nicest mathematically to do. One time I chose the y to get by itself and plugged in. I was very happy because I got a y equals and a function. The other time I chose y because getting the x by itself, the t with the x equation was gave me plus or minus a radical, seemed to be a bit messy, so I went the other way, and sure enough, what I ended up with was a non-function. So here, solve each for t. I don't know that I'm comfortable right now introducing inverse cosine into this situation. So instead of just getting t by itself, what I did was I got cosine of t. So I'm kind of sort of following directions, right? And I'm going to do the same with sine. And now I'm going to go back to, in this instance, prerequisite knowledge, trig identities. You didn't see that coming, did you? What does it mean, trig identities? Well, remember something we did in vector land was talk about how we had linear combinations of these things. So isn't it true that I could take x and add it to y, right? And you have 3 cosine t plus 3 sine t. Well, I don't really want to do that. What I want to do with each one of these separate things is I want to square and get sine squared and cosine squared, and maybe now you'll start to see where I'm going with this. Right now I'm not legal because I squared the left side of each equation. What does that mean I have to do? Yes? Now what? Well, if it's true, right, if x is equal to 3 cosine t and y is equal to 3 sine t, then it is true that x plus y is equal to 3 cosine t plus 3 sine t. Fine, but that wasn't, remember, helpful to me. But I figured out what x squared and y squared were like, right? So if I multiply now both sides by 9, isn't it true that I have x squared, which equals 9 cosine squared t? Are you with me? Right? I just multiplied both sides by 9 here to get x squared by itself. And I'm going to do the same here and get y squared by itself by multiplying both sides by 9. Add y squared. Add y squared. Do you see the identity? Good F word. But what is this? Boom shakalaka. There is not my unit circle, is it? But it is a circle with a radius of what? Not 9. Oh my goodness, that's such a terrible graph. But this is a circle with a radius of 3. OMG. Now, given that I showed you before on your calculator that when in your calculator you put in x to be cosine t and y to be sine t, that you got the unit circle, but after all, that unit circle has a radius of what? 1. This time we did the algebra and we got unit circle with a radius though of 9. What a coinkydink. So can you make a generalization then? can you make a generalization that if x is equal to the radius times cosine of t and y is equal to that same radius sine t, what is that graph going to be? Right? That is going to be a circle, right? With a radius. Crazy. Don't forget that. We'll come back in the future. I'll remind you. All right, kind of cool. Oh. Well, firstly, I'm a little bit annoyed with this +6 and this -5. But also, I just made this big freaking discovery, and what are they doing here? Ugh, annoying. All right, well, let's go through our steps. Right, step 1, remember, was to solve each. Right? But we're going to kind of cheat. And we're not going to get t by itself. We're going to get cosine of t by itself. So what happens here? You get cosine of t, right, is equal to x minus 6 over 4. And what is sine t going to be equal to? Right, you're going to add 5 and divide by 3. Right? Now I'm going to, just like we did before, I'm going to square both sides. And use my identity. I didn't write square both sides before, did I? I just wrote trig identity. Square plus my trig identity. Means I'm going to square and square. You see what's going to happen here? So I'm going to add these together. Right? Cosine squared, do a little bit different. Cosine squared is equal to what? Then, since I had cosine squared and what is it's equal to, now take sine squared, and what is it equal to? Okay, that's swell, but I thought I was supposed to be eliminating, I want rectangular, I don't, oh wait, what is this? Well, there's my trig identity. And I was thinking about squaring all this stuff out, but I don't think I'm going to because I think I recognize this from AAF. Right? Right? See what I'm saying? Right? Do you recognize that? And look, it's equal to 1. Remember all those formulas I gave you where I was like, oh, last year I was like, they have to be equal to 1. This is not a circle. What is it? Good. Remember this terminology? Radiate in the x direction is not the same as you radiate in the y direction. So this is an ellipse. Because it had a plus in front of it. And the center isn't at 0, 0, isn't it? center was at 6, -5. Oh, snap. And if you graph that, right, in parametric form, I can see the ellipse. Oops, I forgot my +6, didn't I? That's my shift. Now my window was kind of messed up, wasn't it? So I just did a zoom trig. What? Oh, right, I was shift off the center. Can you see that's, right? Where did we say our center was? Wow. Gee, I wonder what that center is. All right. Well, that was a whole heck of a lot of fun. So hopefully we've done a bunch of examples now where you see, eliminating the parameter. Now I'm going to go back to vector land for a second. And I'm going to define this vector r in terms of, right, two vectors. Right, so this is vector 1 and this is vector 2. Only vector 2 has a scalar multiplier in front of it. Do you remember that? We did scalar multipliers. Right? Only I called, coincidentally, this scalar t. So I want the component form of r if t are these differing values. So here's what that means. So I'm just going to go up and say, well, what is r? R is -2, 3, plus another vector, but when t is -1. So that means r is -2, 3, plus -1, -2, which means r is actually -3, 1. If I did my math right, check me out there. So -3, 1 is about right there. Can you do the rest? Plus nut and honey, right? Because if you multiply that, so this is just -2, 3. So where's that? -2, 3 is about there. How about this one? Three, 5, if I'm doing my math right. Where is that point? Maybe there. And then finally this one. Can you do this in your head? right? If I put a 2 there, that's going to turn that into 2 and 4. So negative 2 plus 2 is 0. And 3 plus 4 is, what, 7? Oh, whoops, this was a negative 2, wasn't it? My bad. Negative 2, 1. So this is actually a negative 1, 5. Thought something was wrong there. But 0, 7 is certainly about here. So I have negative 1, 5, and then 0, 7. So I want you to think about what I changed here. Every time I started with negative 2, 3, and then I added a multiple of 1 comma 2. So you can kind of sort of think of this as, right, if I'm starting from the origin, I kind of radiated out here, then here, then here, then there, right? But notice where all of those points ended up lying. Oh, that's so bad. So bad. Right? So it was this value of t, right, that told me where in relation to negative 2, 3 I was, right? Like, how did you change from negative 2, 3? Where have I kind of thought about that before? Parametric equations can be used and can be, right, representing an equation of a line. You've already kind of seen this in some of the equations we've done, example we've done before. But what we were doing before really was that very one application where I was saying, parametric equations can be used to represent in quasi-function form something that's not a function, which is not that useful to you now, but will be. And also that hidden version of that hidden time component, like where is a particle at time 0, at time 1, at time 2 along this particular path. So now I want to represent something old, right? Given 2 points, find the equation of a line. But I want you to find the parametric form of the line. So let's say I have 2 random points, A and B. Now I have another non-fixated point, P, along the same line. O star stands for the origin, so starting at the origin, I want to come up with a vector that goes from the origin out to any point. So A is fixed, B is fixed, but P can roam along this line, anywhere along this line. Any x and y on that line. So there's a vector that goes from the origin out to that point. If I draw another vector out to A from the origin, that vector is OA. Now, given this information, how would I generate that? Right? Let's say A was at the point, what, negative 3, 1. This, of course, is 0, 0. So are you okay with the point that, okay, saying that OA is just my components of A, right? A1 minus 0 and A2 minus 0. But how about the purple one? What's the purple one? What is A going out to this movable point P? AP. Well, I don't know. But I do know what AB is, don't I? AB would just be right? It's just taking, right, B minus A and B1 minus A1, B2 minus A1, isn't that piece? And then this whole idea of the scalar multiple, isn't wherever this point P is a scalar multiple of AB? Using our resultant vectors, right, knowledge about resultant vectors, if I add OA tip to tail with AP, I do get the red vector OP. But then introducing this idea of a scalar multiple, AP is some scalar multiple of this AB, which I can get a representation, a numerical representation for. So I'm going to replace AP with a scalar times AB. Because remember, point A and point B were fixed for me. Now, I'm sorry, I know this might be, I'll do an example with actual numbers first, next. So, the vector form of that line, where I can generate any x and any y, comes from OA, right, going from the origin out to the first point, plus a scalar times the vector AB. And all of this information I can get from my two given points. Represent the vector going from O to the given point A, and then create the vector AB, again from 2 points given to you, A and B. Wow. Think of the first vector as your position vector. This nails you in space, right? Nails you down at point A right here. So that's the position vector. Then the direction vector tells you from 2, -3, where are you going to land depending upon that scalar. Am I going to land there? So scaled back, scaled maybe by a half, not scaled at all, scaled by maybe 1.5, scaled by maybe 2. All right, let's do an example with some numbers. And this is weird, I know. So find a parametrization. That's a hard word to say. Parametrization, which means find me the equation of a line in parametric form. Through point C and point D. I think I should have just used A and B, don't you? Don't worry about these two things yet. Let's just worry about this first line. So first I would suggest draw. -5, 2. And 1, 4. I want to find a parametric version of this linear function. Okay. So remember, my goal is to be able to write an expression such that any random point can be generated from my equation, and I will be along this line. So my goal is to write any xy is equal to the first point, create the first point C, turn it into a vector from the origin. So technically you're doing -5, 0, and 2, 0. That's my position vector. Right, there's my position vector. And then I'm going to add my parameter times my direction vector. How do I move? What direction do I move along that vector? And for that, you're going to go to your second point, and you're going to create the vector CD. Sorry, this is kind of messy. So 1 minus -5, 1 minus -5 is 6, and 4 minus 2 is 2. So cleaning that up, initial position when time is equal to 0, and then when you change time, that is just a scalar of the vector 6, 2. Whoops. So that's my parametrized equation, which of course I could write like this. Do you see where that came from? -5 plus t times 6. How would you write the y component then? The y component is 2 plus what? Yeah, 2t. So a third way I could write this is and a fourth way I could write this oh, my Lanta, right? Great. What does it mean? So what it means is, let me do this even different. This point P, how I can find it as I move T, right? I can choose T, and like for instance, what if I say when T is equal to 1, what is happening? Right, when T is equal to 1, I have -5 comma 2 plus 1 times 6 comma 2. And maybe you, right, what is that equal to? So it's -5 plus 6, which would be 1, and 2 plus 2, which would be 4. Oh, shocker. That lands me Here, 1, 4. That was, I know that's on the line. That was one of the points that was given to me. Crazy. What about when t is equal to -1? What would you have? Right? Start with the position -5, 2. Add the scalar -1 to the vector 6, 2, which of course gives you -2. I'm sorry, -6, -2. What does that result in? Right? Where is that point? Oh, way back here, but it would be along this line. So when asked for the parameterization, I don't care whether you give me this form, this form, this form, or this form. Give me any form that you like, unless unless you're matching multiple choice or I don't know. I don't know how I would even dictate which one you give me if I in a written form if I really wanted. All right, now let's look at these other two. What are they asking? Give restrictions. So remember I talked about how the parameter t, the hidden parameter, can kind of be limiting, right? So what I want you to do is limit t such that I only get the line segment between these. So that would be only here. I want you to limit t so that the graph I get only goes between point P and point D. So, I mean, you could do some guessing and checking, especially with some easy, with these numbers are fairly simple, but here is the process. It goes back to pre-algebra. The domain that I want is from my x1 to my x2, and the range I want is from my y1 to my y2. So if I want x to be between -5 and 1, what is my x component? Hello, right? Algebra 1. Add 5, whoops, to both sides. Now I'm really hoping the same thing happens with the y, right? But if I want to check my work, if I want y, remember, because the t is the same, I need y to be between 2 and 4, but my y component is 2 plus 2t. And I think you can see that you get the same thing, right? Yay! So if you go to your calculator and you put this into x1 and this into y1, and you make your x min and max the domain and your y min and max the range, you should see this line segment. Oh, and sorry, and make your t go between 0 and 1, you will see this. So -5 plus 6t, oops, -5 plus 6t, and 2 plus 2t. I'll be ready shortly. I'll be ready shortly. I forgot my range. What was it? I mean my domain. -5 to 1. Maybe I'll do -10 to 10, huh? Ah! There's kind of a hurtin' looking, right? But notice that when t is equal to 0, I'm at -5, 2. And then as I increase t, it stops me right at 1, 4. Pretty cool. All right. Lastly, given the parametrically defined curve, oops, I forgot to put that in. I'll tell you what it is. Oh no, I did here. Given the parametrically defined curve below, is what that's supposed to say, find the value of the parameter t that produces the graph in the indicated quadrant. And then I did forget to put the quadrants. So here's what I'm looking for. In Quadrant 1, right? Quadrant 1, that's the only portion of the graph I want to see. So I'm asking, how would you restrict t so that if you put it into your calculator, I would only see that little piece? So in Quadrant 1, what has to be true about x? What is true about x? X is positive, strictly positive, right? To be in the quadrant, you can't be equal to. And isn't it also true that y needs to be greater than 0? Now again, I could figure this out from the picture, but I just want you to show you the procedure. So here is my x component, and here is my y component. So in order to guarantee that x is greater than or equal to 0, 1 minus the absolute value of t needs to be greater than 0. And then the y component, t minus 1/2, needs to also be greater than 0. And this has to be inclusive, right? Like my restriction on t has to satisfy for both the x and the y. So this is not a problem. T has to be greater than 1/2. Cool. But this gosh darn absolute value, do you remember what that means? So if I just do this technically, first I subtract 1 from both sides, then I divide or multiply by a -1, which do you remember what that means to do? So what does it mean for the absolute value of t to be less than 1? It means the distance from 0 has to be less than 1, which means t has to be between -1 and 1. What if I put this on this is again an Algebra 1 objective. If I put this on a number line, I would have an open circle at -1 and all the numbers through open circle at 1. But wait, I have to also right? That's my x component. My t has to also satisfy this, that t must be greater than a half. Open circle on a half. So what does that mean for my t? My t actually, shut up, Dylan. My t actually, the t that satisfies both conditions, is t needs to be between a half and 1. Quadrant 1. Let's go check this out on our calculator. Let's start with my square window. Oh, my lanta, what is that? Oh, wait a second. I need to go from, right? I have to set my t. What t do we just find? What t do we just say? 0.5 to 1, right? I'll change my scale to a half, my x scale too. Whee! Let's see what I get. Oh, I can kind of see it. I can kind of see it. Can you? Let's shrink this a little bit more. And I don't, yeah, oh crap. What I do, what I do. Oh, -2, right? I am, people, when you want to know, well, what should I put my window to? Experiment. That's all I'm doing. Right? 0.5 to 1. Right? 0.5 to 1. All right. What picture, I'm sorry, what t, what t do I need to only get what's in quadrant 2? Right? I only want that portion. So we're going to do, in quadrant 2, x has to be negative, but y is positive. So we already know the t value that makes y positive, right? T needs to be greater than a half. But how about to make x less than 0? Right? 1 minus the absolute value of t needs to be less than 0. What does it mean to make t greater than 1? That means that the distance from 0 needs to be bigger than 1. So that means t needs to be less than 1, or, not an and. So what does that look like on this graph? -1, right, is all down here. It's an open circle is what that's supposed to be. Open circle, arrow. And then 1 also has an open circle. and to the right. That takes care of this, but what about this one? That's still right. Where's my overlap? Right, my overlap starts at 1. Oh, that's not completely right, is it? Look at the picture again. So I'm okay with t starting -1. I'm sorry, t being 1 gets me here. But then if I just keep going, I don't stop here. Where is this? Right? What point is this at? Well, I didn't give you enough information at the beginning of the problem. But that's because I didn't finish this slide, as you can see here, right? I didn't indicate the quadrants yet, and I didn't tell you that the original t was between -3 and 3, right? So that's the original t that I gave you for this picture. So it's not enough to say t needs to be greater than 1. Given my original t restrictions, right, t does need to be greater than 1, but can't go beyond 3. Why do I have the equal sign there? Because I had the equal sign here, that's why. Okay, so that gets me just this piece. The t being greater than 1 got me into the second quadrant, but then I had to stop, right, to get this picture. So hopefully you can see that this is exactly what I'm going to do for the next quadrants. Right? With each time I got to say what has to be true. In quadrant 3, x needs to be less than 0. Y also has to be less than 0. So we've already figured out what t has to be to make x less than 0. To make y less than 0, we haven't come across that yet, but I think you can figure out, right? If t minus 1/2 needs to be less than 0, then t needs to be less than 1/2. And if I graph that, there's my -1 and 1. And then my overlap is going to be starting, well, 1/2 is here, and I'm going to have the open circle in here. So what am I going to have this time? Because in reality, right, this stops at -3 and at 3. Right? And again, that comes from up here. I apologize for not giving that to you at the beginning. I just don't know why I started my video without finishing this slide. But anyway, hopefully you can see that what I have here then for quadrant 3 less than or equal to -3, but strictly less than 1/2. Oh, I'm sorry, not 1/2, -1, right? Right, I can't include, I didn't start to overlap until -1. Lastly, quadrant 4. What's true in quadrant 4? X has to be positive, Y has to be negative. So for the x greater than 0, right, we took care of that in quadrant 1, right, and we found that t needed to be between -1 and 1. And for y to be less than 0, we just did that in quadrant 3. T needs to also be less than 1/2. My original t stopped at -3 and 3. And then my first restriction is that I need to be between -1 and 1. Whoops. Right, that covers this one, but then at this I also need to be less than a half. So where is that? So the overlap is right here. Strictly less than -1. I'm sorry, strictly greater than -1, strictly less than 1/2. Well, sometimes kids will ask me, can I put this into, your bracket form? And the only thing you have to be careful of, remember, because we've got this extra parameter now, you need to make sure you're telling me that you're giving me t values. So if you wanted to put, right, this in, just tell me you're dealing with t, right? This one would be what? Square bracket, -3, soft bracket, -1, so on and so forth. It is much more common to use the inequality notation here. All right, that's it for today.